Well, welcome to our last video on Chapter 3. This will cover Section 3.4 on process control and a few little things from Sections 3.5 and 3.6. As always, please read your book to make sure that you get all the information that we're not necessarily including in the videos. So, in this video, we'll be covering process control, specifically modes of execution, process creation, system interrupts, mode switching, and change of process state. Most processors support at least two modes of execution. The less privileged mode is often referred to as the user mode because user programs are typically going to execute in this mode. The more privileged mode is referred to as the system, control, or kernel mode. The last term refers to the kernel of the operating system, which is the portion of the operating system that encompasses important system functions. Certain instructions can only be executed in this more privileged mode. These include reading or altering a control register, such as the program status word, primitive input-output instructions, and instructions that relate to memory management. In addition, some regions of memory can only be accessed in the more privileged mode. To recap for just a moment, the kernel handles things like process management, memory management, input-output management, and support functions such as interrupt handling and monitoring. Take a look at Table 3.7 in your textbook to get a more complete idea of what the kernel does. So let's talk about what the operating system does to create a new process. The good news is we've covered most of this in our previous videos, so we'll just quickly go through the list. It assigns a unique process identifier to the new process, allocates memory space for the process, initializes the process control block, sets the appropriate linkages, and what we're talking about there is if the operating system maintains linked lists corresponding to the states in the 5-state process diagram, it would add the linkages to put the process into the appropriate list, ready, running, or blocked, and creates or expands any other data structures that the operating system might use to keep track of its processes. Remember that while all operating systems have certain commonalities in the way they handle processes, they are all different and may have different ways of doing things that require those other data structures. Now, in previous videos, our primary example of something that will cause processes to switch in and out of the running state is the expiration of the time slice. Basically, the process in the running state has had its time to operate, and now it's time to clear out of the running state and give someone else a turn. Now we're going to talk a little bit more specifically about the types of interrupts that will cause processes to switch. Now we'll get a little more specific on some mechanisms that will cause a process switch. First of all, we have an interrupt, and by the way, the timeout that we've been talking about in previous videos counts as part of this mechanism. It's external to the execution of the current instruction, and basically it's a reaction to an asynchronous external event. A trap is associated with the current instruction that's executing, and it's for handling an error or an exception condition. And a supervisor call is an explicit request to an operating system function. Now let's talk a little bit more specifically about interrupts and traps. An interrupt is something that happens due to some sort of event that's external to and independent of the currently running process. We can have a clock interrupt, input-output, a memory fault, and again, our time slice is the maximum amount of time that a process can execute before being interrupted, and that's where that timeout interrupt comes from in previous videos. A trap occurs when an error or exception is generated within the currently running process. It's the operating system that'll determine if this condition is fatal. If it is, it'll be moved to the exit state and the process which occurs, and action will depend on the nature of the error. Now, let's think back to our user mode and kernel mode processes. We can switch back and forth between these depending on what's going on. So let's talk about when we're going to switch from user mode to kernel mode in a process. Now, if there are no interrupts pending, we're basically okay. We can proceed to the fetch stage and fetch the next instruction of the current program in the current process. If, however, we do have an interrupt pending, we set the program counter to the starting address of an interrupt handler program and switch from user mode to kernel mode so that the interrupt processing code can include privileged instructions, which, recall from previous slide, only the kernel mode processes are allowed to execute. Now, switching a process from user mode to kernel mode doesn't really require that much overhead. Switching a process into another state, from ready to running, from running to blocked, etc., involves a lot more overhead. This graphic shows what the operating system has to do to make that happen. We save the context of the processor, update the process control block, move the process control block to the appropriate queue, select another process for execution, update the process control block of the process that we've selected for execution, update memory management data structures, and restore the context of the processor to that which existed at the time the selected process was last switched out. Now, because there's so much effort involved in a state change, the operating system has to do a bit of a balancing act, because we want all of the processes to appear to be moving forward and making progress at the same time. On the other hand, we can't switch out too quickly because it takes so much effort and so much overhead to do so. Now, let's finish up Chapter 3 by talking just a little bit about process control in UNIX. A new process is going to be made by using the kernel system call fork. This allocates a slot in the process table for the new process, assigns a unique ID, makes a copy of the process image of the parent minus any shared memory, increments the counters of any files owned by the parent to indicate that another process also owns them, assigns the child process to the ready-to-run state, and returns the ID of the child to the parent and a 0 to the child. Now, once the child process has been created, the kernel can stay in the parent process, transfer control to the child process it just created, or transfer control to another process altogether. And that finishes up Chapter 3. Our next set of videos will be continuing in our operating systems book and covering Chapter 4.